In this example, a simulation of surface water-groundwater coupled modeling is presented. The model area is around Barron Lake located in Niles, Michigan. The general model setup includes DEM is used for the groundwater aquifer top, and the IGW rock top raster based on well records is used as the aquifer bottom. Michigan wellogic borehole data is used to create a 3D TP model in this area using a different software. This 3D TP model is imported into IGW to create a 3D conductivity field. Barron Lake is modeled as a surface water lake. A pumping well that is located near the lake pumps water from the aquifer into the lake. There are lake level measurements available from 2006 to 2013, and groundwater monitoring has been carried out at 11 private wells since 2013. Only measurements in 2013 are used to calibrate the model, and the groundwater monitoring wells can be used to infer transient boundary conditions around the lake. The groundwater transient boundary condition is modeled as a polygon river and is stored as a shapefile. A domain polygon that approximates to a customized watershed based on the DEM map around the Barron Lake is stored as a shapefile. Start up IGW and click the last button in the top toolbar of the Google Map window to toggle to the GIS importer. Click Add New Modeling Layer to add a domain polygon from a shapefile. Add river polygons for the groundwater boundary condition from a shapefile. Click Add New Mapping Layer to add a well location shapefile. Highlight one of the modeling layers and click Draw a Selection box to select the domain polygon and the river polygons. Click Extract or Import Model feature from GIS to IGW to add these polygons to the IGW main window. Automatically, the extent of this polygon will be used as the workspace extent. In the IGW main window, click Select/Edit Zone and right-click the domain polygon to open up a pop-up menu. Go to Add Streams and Lakes to this polygon to open a Streams/Lakes extraction window. Check Lakes and then check Very Large, Large, and Middle and click OK. IGW will automatically search for any available lakes in this polygon from the IGW server. In this example, there is one lake found in the domain polygon, which is Barron Lake. Answer yes to import this lake polygon into IGW, or no to discard the polygon as a shapefile. We now have all of the polygons ready to be updated with the appropriate attributes and properties. Select the domain polygon, Zone 2, to edit attributes for this polygon. Check the Conductivity box in the Flow Properties tab and select Borehole Simulation. Click the button right next to it to open a transition probability simulation interface and click Load Existing Realization to load an existing TP model result. Change the typical conductivity value for material 1 from the default value to 53, then click OK. Continue to assign the other flow properties. Check Top Elevation in the Elevation tab and select Raster. By default, the DEM from the IGW server is used. There are several DEM datasets with different resolutions available in the IGW server. Check the bottom elevation and then select Raster. By default, the rock top elevation raster from the IGW server is used. In the Sources and Sinks tab, click the Head-Dependent Flux subtab. Check the One-Way box and select the Top Elevation option to make the whole surface capable of functioning as a drain. Click the Prescribed Flux tab and check Recharge, then select Raster to use the IGW recharge data. Click the Overland Flow button to bring up the Surface Water Overland Flow Options window and check Overland Flow. In the Climate tab, select From Rain Gauges and click Edit/Load from File to open a rainfall station time series window. Then select From IGW Raster to use the daily rainfall data in the IGW server. Do the same thing for the maximum temperature and the minimum temperature. In the Land Use and Cover tab, select Raster and use the IGW dataset. In the Soil Type tab, select Raster and use the IGW dataset. Click Lookup Table to open the soil type lookup table and change all default values in column CTA0 to -1. This means the initial moisture content will be given from a moisture content file. In the Root Zone Depth tab, check Root Zone and select Raster and use the IGW dataset. In the Snowpack tab, check all boxes to turn on the Snowpack module. In the Evaporation tab, check the EVT box and select Priestley-Taylor equation to turn on the evapotranspiration module. For the Barron Lake polygon, select the Source and Sinks tab and check two-way in the head-dependent flux subtab. Check From Coupled Surface Water Modeling and click the button next to it to open up a Surface Water Dynamics window. Select Transient and click it to import the flow that is added to the lake. There are lake level measurements available, so check Stage Measurement and click the button next to it to import the lake level measurements from a file. Assign a constant leakance for the lake. There is a bathymetry raster available for Barron Lake, so select From Raster File in the bottom elevation box to load the file. For the river polygons used as the groundwater boundary condition, follow the same steps below for each of the 7 polygons. Select the polygon, click on the Source and Sinks tab, and check two-way in the head-dependent flux subtab. In the Stage box, select Constant, check Transient, and click it to import a transient stage from a given file. In the bottom elevation box, select Constant and assign 200 feet in the input box. In the Leakance box, select Constant and assign a high value, such as 5,000. In Attribute Explorer, click Layer 1 and the Surface Water Channel button to bring up the Surface Water More Options window. Check the Surface Water Infiltration as Groundwater Recharge box and the Import Initial Soil Storage box. Click the File button to load an existing moisture content file. In the Overland Solver box, select Non-Process Based to use the IGW Recharge module. Click the label More/Less to customize the recharge model output controls. This northeast well is the pumping well. In the main menu, click Add Well to add a pumping well, and the exact location of the well can be manually input. Modify the well screen location. This pumping well is assumed to be a deep well. Import the pumping rate from a given pumping file. Click the clock icon to set up a transient model. The simulation will start from 06/25/2013. The global time step used in this example is 1 day. A time step of 1 day is fixed in the recharge model, and the simulation length is 138 days. Discretize the model. Note that there are 5 computational layers used in this example. Customize the display layers. Add a monitoring well to observe the transient processes of the groundwater and surface water parameters. Rediscretize the model and open the monitoring well window and select a parameter to show. Customize its location and size. Before running the model, we need to turn on the lake coupling by clicking the Numerical Solver Settings icon in the Flow tab, then check the Lakes box in the Surface Water Modeling box. IGW allows the user to stop or pause the model at any time to customize the display of the results and charts. We can see that the calculated lake levels match well with the measurements. The lake mass balance bar chart applies to the whole lake, and it represents the lake mass balance for the current time step only. The transient lake dynamics can be saved as a text file. The temporal data of every component of the lake dynamics will be included in this file, such as flux to or from the groundwater, precipitation, evaporation, etc.